What if the ultimate act of creation wasn't a beginning but an ending? What if the singular moment you and I call the Big Bang, that brilliant universe-forging detonation, was merely the afterglow of something far stranger, far faster and infinitely more violent? For decades we have told ourselves a story, a magnificent evidence-based story of our cosmic origins, a story that begins in a state of unimaginable density and heat, a single point smaller than any atom containing all the energy and potential of the 100 billion galaxies that would one day grace the darkness. Then, in an instant that defies all earthly comparison, it erupts. This is not fire as we know it, not an explosion moving through space, but the explosion of space itself. It is the birth of time, the genesis of direction, the unfurling of the very dimensions that would define reality. In this primordial furnace, hotter than the core of a trillion stars, the fundamental laws of physics are being written. Forged in a crucible of pure energy, the universe is a searing incandescent plasma, a seething soup of elementary particles popping in and out of existence, a symphony of creation playing its opening chord. For the first few 100,000 years, this cosmos is a blinding fog of light and matter, locked in a gravitational dance. No stars, no galaxies, no planets. Just a brilliant expanding haze cooling with every passing microsecond, as the fabric of space-time stretches ever onward, ever outward. This is the Big Bang Theory, and it is one of the greatest intellectual achievements in human history. It is not a guess. It is not a fable. It is a scientific masterpiece built upon a foundation of rigorous mathematics and confirmed by startlingly precise observations. It was this theory that predicted decades before we had the technology to see it that the universe must be expanding. It foresaw a cosmos where galaxies are not static islands in a placid sea, but cosmic ships fleeing from one another in the wake of that initial powerful impulse. And then in the 1920s, astronomer Edwin Hubble pointed his telescope toward the heavens and saw exactly that. He witnessed the light from distant galaxies stretched reddened by their journey across an expanding universe, confirming the theory's most audacious claim. The universe was not eternal and unchanging. It had a history, a birthday, and it was getting bigger every single day. The theory made another, even more specific prediction. A whisper from the dawn of time that should still be echoing through the cosmos today. It calculated that the intense heat of that initial fireball, though cooled by 13.8 billion years of expansion, shouldn't have vanished entirely. It should persist as a faint cold background glow a relic radiation permeating all of space, a fossil of creation's first light. For years this was pure speculation, a ghost in the mathematical machine. Until in 1964, two radio astronomers in New Jersey were trying to eliminate a persistent annoying hiss from their antenna. They pointed it everywhere, they cleaned it. They chased away pigeons, but the hum remained. It came from every direction at all times with the exact same intensity. What they had stumbled upon in one of history's greatest accidents was the echo of the Big Bang. The cosmic microwave background radiation. It was the afterglow of creation cooled to a mere 3 degrees above absolute zero, and its discovery cemented the Big Bang as the undisputed story of our universe. From this single powerful idea, we could explain why the universe is overwhelmingly composed of the lightest elements, hydrogen and helium. In the first 3 minutes, the cosmos was a nuclear furnace cooking these simple atoms in precisely the ratios we observe in the oldest stars today. The theory works. It tells a coherent, consistent, and breathtakingly beautiful story. It connects the largest structures we can see, the superclusters of galaxies stretching for hundreds of millions of light years, to the fleeting quantum chaos of the very first second. We should have declared victory, closed the book, and celebrated our profound insight into the nature of reality. But science is not about celebrating what we know, it is about relentlessly questioning it. And as we looked closer at the stunning success of the Big Bang model, we began to see cracks. Not small fissures, but deep chasm-like paradoxes in the foundation. Mysteries that the Big Bang, for all its power, could not solve. It gave us a magnificent picture of the universe's evolution, but it left the most critical questions about its initial state unanswered. It described the eruption perfectly, but it couldn't explain the volcano. The first great mystery is one of impossible uniformity. Look out at the night sky in any direction. The faint glow of the cosmic microwave background, that relic of the early universe, is there, and the astonishing thing is its temperature. It is almost exactly the same everywhere you look. To the north it's 2.725 degrees Kelvin. To the south, 2.725 degrees. To the east to the west, it's the same story. The tiny fluctuations, just one part in 100,000, are the seeds of galaxies, but the background itself is a canvas of almost supernatural smoothness. To appreciate how bizarre this is, you must understand a fundamental rule of the cosmos, the speed of light. Nothing, not even information, can travel faster than light. Now imagine two distant regions of the observable universe, one on your far left horizon and one on your far right. Today they are separated by more than 90 billion light-years. When the light of the cosmic microwave background was released about 380,000 years after the Big Bang, these two regions were still separated by millions of light-years. According to the standard Big Bang model, there simply has not been enough time in the entire history of the universe for a signal array of heat, or any kind of information to travel from one of these regions to the other. They have never been in contact. They have never been able to exchange energy to even out their temperatures. They are and have always been causally disconnected strangers living on opposite shores of the cosmic ocean. Yet they have the same temperature. Not just similar, but the same down to an almost unbelievable precision. How it's like finding two people on opposite ends of the Earth who have never met, never spoken, never had any contact yet, who are precise, identical twins down to the last molecule. It makes no logical sense. For them to share the same properties, they must have originated from a common source, or been in communication at some point. Within the confines of the Big Bang story, this is impossible. The universe appears to have a shared thermal memory that it has no right to possess. This isn't a minor detail. It is a profound violation of causality, the principle that a cause must precede its effect. Scientists call this the horizon problem, and it suggests our cosmic story is missing its first and perhaps most important chapter. It's as if a grand symphony began playing in perfect harmony across an entire continent, simultaneously, without a conductor, and without any of the musicians ever having rehearsed together. Something in the very earliest moments must have connected these now distant regions. Something must have synchronized the universe before the Big Bang we know even got started. The second mystery is carved into the very geometry of space itself. According to Einstein's theory of general relativity, mass and energy curve the fabric of space-time. The universe, therefore, can have one of three possible shapes on the grandest scale. It can be closed, like the surface of a sphere with a destiny to one day stop expanding and collapse back on itself in a fiery big crunch. It could be open, shaped like a saddle destined to expand forever, tearing itself apart until it becomes a cold, empty wasteland. Or it could be perfectly, exquisitely flat. This flat universe is the knife's edge between the other two possibilities. It represents a universe with a very specific, critical density of matter and energy, one that will also expand forever but slow down gracefully over an infinite amount of time. Any deviation from this perfect flatness in the early universe would have been magnified exponentially over 13.8 billion years. If the early universe had even a fraction more than the critical density, a number infinitesimally larger than 1, it would have been so curved that it would have recollapsed into a singularity after just a few million years, long before the first star could ignite. If it had a fraction less, a number infinitesimally smaller than 1 space, would have expanded so violently and so quickly that matter would have been flung apart too dilute to ever coalesce. Gravity would have lost the fight from day one, and not a single galaxy, star or planet would have ever formed. The cosmos would be a thin, lonely, featureless void. For us to be here, for galaxies to exist, for life to have a chance, the density of the early universe had to be tuned to the critical value with an accuracy that beggars belief. The required precision is equivalent to balancing a pencil on its sharpened tip and having it remain perfectly upright without falling for 13.8 billion years. It's like firing a cannon from one side of the observable universe to the other and hitting a target the size of a single atom. And yet, when we measure the geometry of our cosmos using the cosmic microwave background and the distribution of galaxies as our cosmic rulers, we find that it is against all odds breathtakingly flat. The universe is balanced on that impossible knife's edge. Why? The Big Bang Theory offers no explanation for this miraculous fine-tuning. It simply assumes this perfect initial condition as a starting point. It's like coming across a pencil standing perfectly on its tip and saying, well, it must have just started that way. This is not an explanation. It is an admission of ignorance. This extraordinary coincidence, this flatness problem, suggests that some powerful mechanism in the universe's first moments didn't just accept the initial conditions, it actively forced them into being. Some cosmic process must have stretched and flattened the fabric of space-time, ironing out any primordial curvature with unimaginable force, leaving it as smooth and geometrically perfect as a flawless sheet of glass. The universe isn't flat by chance. It appears to have been driven to flatness. The third and perhaps most exotic mystery comes not from what we see, but from what we don't. Our most successful theories of fundamental physics, the so-called grand unified theories or GUTS, predict that the extreme energies of the early universe should have produced a menagerie of strange exotic particles. These are not the familiar protons and electrons of our world, but heavy stable relics from that initial inferno. The most prominent among them would be magnetic monopoles. Think of a simple bar magnet. It always has two poles, a north and a south. If you cut it in half, you don't get a separate north and a separate south. You just get two smaller magnets each with its own north and south pole. A magnetic monopole would be an isolated north or an isolated south pole, a fundamental particle carrying a basic unit of magnetic charge, just as an electron carries an electric charge. According to our best theories, the cooling of the universe after the Big Bang should have been like water freezing into ice. As the universe cooled and underwent phase transitions, defects should have formed in the fabric of space-time, just as cracks and imperfections form in ice cubes. These defects would be the magnetic monopoles, and they should have been produced in colossal numbers. They would be incredibly massive and stable relics from the first trillionth of a second. The universe, therefore, should be littered with them. They should be everywhere, a form of cosmic shrapnel from the moment of creation so abundant that their collective gravity would vastly outweigh all the stars and galaxies we see. Their magnetic influence would be undeniable. But we have never seen one. Not a single solitary monopole. For decades, physicists have built elaborate detectors deep underground, shielded from cosmic rays, waiting patiently to catch just one of these predicted ghosts. The search has yielded nothing. An absolute deafening silence. It's as if a world-ending volcanic eruption was predicted to blanket the globe in a thick layer of ash, and yet when we look, the skies are perfectly clear. There is not a single speck of dust to be found. Where did all the monopoles go? The Big Bang Theory, when combined with our best understanding of particle physics, leads us to a definitive and spectacular contradiction with reality. It predicts a universe that looks nothing like the one we inhabit. This is the monopole problem, and it is a stark signal that our story of a simple, hot, expanding beginning is missing a crucial piece of its plot. So we stand at a precipice of understanding. We have a triumphant theory, the Big Bang, that accounts for the expansion of the universe, the primordial elements, and the fossil light from creation's dawn. It is a monumental human achievement. And yet it leaves us with three colossal paradoxes. The horizon problem asks how the universe became so uniform without communication. The flatness problem asks why its geometry is so impossibly balanced. The monopole problem asks where all the predicted exotic relics have gone. These are not minor inconsistencies. They are fundamental flaws in the narrative pointing to a profound gap in our knowledge right at the very beginning. They tell us that the hot, dense state we call the Big Bang could not have been the ultimate origin. It must have been preceded by something else. A process capable of connecting the disconnected, of flattening the curved, and of clearing out the unwanted debris of creation. We need a prequel to our cosmic story. A mechanism that could take a chaotic, lumpy, and wildly unpredictable infant universe, and in a flash of incomprehensible power, prepare it for the grand drama that was to follow. We need an event that happened in the first sliver of a second, a moment so brief it makes the rest of the Big Bang seem like a slow, leisurely affair. Scientists now believe they have found this mechanism, a theory of such mind-bending scale and consequence that it doesn't just solve these three great mysteries, it completely redefines our concept of a beginning. It proposes a burst of hyper-accelerated exponential expansion a cosmic growth spurt of such violence it would make the Big Bang itself look like a gentle sigh. An event called cosmic inflation. What if in the first fraction of a nanosecond, our universe swelled from a size smaller than a proton to something larger than a galaxy, driven by a bizarre and powerful form of anti-gravity? What if that split second of unfathomable expansion is the true secret to everything we see and everything we are? What if one of our greatest scientific triumphs was also a profound three-part riddle? What if the very theory that explained the origin of everything, the Big Bang, contained within its elegant mathematics a series of paradoxes so deep they threatened to unravel the entire cosmic story? This was the extraordinary situation cosmology found itself in during the latter half of the 20th century. The picture of our expanding universe born from a singular fiery point was an intellectual monument, a testament to human curiosity. It was built upon the shoulders of giants' minds who dared to apply their equations to the whole of reality. We can trace its genesis to the stubborn genius of Albert Einstein, whose new theory of gravity, general relativity, first gave us the language to speak of space-time as a dynamic, evolving entity. Yet Einstein himself recoiled from the implications. His equations suggested a universe in motion, either expanding or contracting, a notion so unsettling to the prevailing view of a static cosmos that he introduced a cosmological constant, a fudge factor he would later call his greatest blunder, just to hold it still. But the equations would not be denied. The Russian mathematician Alexander Friedmann and the Belgian priest and astronomer Georges Lemaitre, working independently, embraced the truth hidden in the math. They saw what Einstein initially could not: a universe with a history, a universe that had a beginning. Lemaitre, with breathtaking foresight, envisioned a day without a yesterday, a primeval atom from which all space-time and matter erupted. This was the seed. And it was a seed that blossomed into a magnificent tree of evidence. Edwin Hubble's monumental discovery showed us that the galaxies were indeed rushing away from us, proof of an expanding space-time. The work of George Gamow and his colleagues predicted that the afterglow of that initial fire should still be detectable, a faint cold radiation filling all of space. Then in 1965 came the stunning confirmation. Two radio astronomers, Arno Penzias and Robert Wilson, trying to eliminate a persistent annoying hiss in their antenna, had accidentally discovered the echo of creation itself, the cosmic microwave background. It was a moment of supreme triumph. The Big Bang theory had made a bold, specific and falsifiable prediction, and it had been proven spectacularly correct. The theory became the bedrock of modern cosmology, the grand narrative of our origins. But as we look closer at this beautiful picture, as our observations and theoretical understanding sharpened, we began to notice that the canvas was flawed. Deep, unsettling inconsistencies began to emerge, not at the edges but at the very heart of the theory. The triumphant celebration began to give way to a quiet, creeping sense of crisis. The model that explained so much seemed to leave the most fundamental questions unanswered, replacing them with a trio of cosmic coincidences so unlikely they bordered on the miraculous. This was the dawn of a new quest, driven not by what the Big Bang explained, but by what it so profoundly could not. The first and perhaps most haunting of these puzzles is woven into the very fabric of that faint afterglow Penzias and Wilson had found. The cosmic microwave background, or CMB, is the oldest light in the universe, a snapshot of the cosmos when it was a mere 380,000 years old. Before this time, the universe was an opaque, searing plasma of protons and electrons. But as it expanded and cooled, electrons and protons could finally combine to form neutral atoms, an event called recombination. Suddenly light was set free. Photons, which had been trapped in a cosmic game of pinball, could now travel unimpeded across the universe. For 13.8 billion years, that light has been streaming through space, its wavelength stretched by cosmic expansion from a brilliant visible glow into the cool, invisible microwaves we detect today. When we map this ancient light across the entire sky, we are creating a baby picture of the universe. And what that picture shows us is staggering. It is a canvas of almost perfect, almost supernatural uniformity. The temperature of the CMB is the same everywhere we look, to a precision of 1 part in 100,000. From one direction in the sky to the complete opposite, the temperature is a near-perfect 2.725 Kelvin. At first glance, this might seem perfectly reasonable. If the universe started as a hot, dense soup, you would expect it to reach a uniform temperature, just like a cup of coffee cooling in a room. But here our intuition fails us spectacularly, because it runs headfirst into the ultimate speed limit, the speed of light. Think about two opposite points in the sky as seen from Earth. The light from point A has taken 13.8 billion years to reach us. The light from point B on the opposite side has also taken 13.8 billion years to reach us. This means the total distance between point A and point B today is nearly 28 billion light years. But remember, the universe itself is only 13.08 billion years old. There's not been enough time in the entire history of the cosmos for a light signal or any causal influence to travel from point A to point B. They have never been in contact. They have never had the chance to exchange heat, to mix, to settle into thermal equilibrium. They are and have always been outside of each other's causal horizon. Imagine two people on opposite sides of a vast soundproof room. They have never met, never spoken, never seen each other. And yet when you ask them to independently write down a 1,000-page novel, they produce identical texts, word for word, comma for comma. You wouldn't call this a coincidence. You would rightly suspect some hidden connection, some prearranged plan, some information that was shared before they entered the room. The cosmic microwave background presents us with this exact scenario on a cosmic scale. How did these causally disconnected regions of the early universe know to have the exact same temperature? The standard Big Bang model offers no explanation. It simply demands that we accept this as an initial condition, an act of cosmic fine-tuning so precise it felt like a cheat. This profound enigma became known as the horizon problem, a deep crack in the foundation of our cosmic understanding, suggesting a crucial piece of the universe's earliest moments was missing from our story. As if this impossible uniformity were not enough, another equally baffling puzzle emerged from the very shape of space itself. Einstein's theory taught us that mass and energy curve space-time. The universe as a whole must therefore have a geometry, a shape determined by the total amount of stuff within it. There are three fundamental possibilities. If the density of the universe is high, space-time would be positively curved like the surface of a sphere. In such a closed universe, parallel lines would eventually converge, and the cosmos would one day stop expanding and collapse back on itself in a big crunch. If the density is low, space-time would be negatively curved like the surface of a saddle. In this open universe, parallel lines would diverge, and the cosmos would expand forever, at an ever-increasing rate, becoming cold, dark and empty. Between these two destinies lies a third very special case. A universe with a critical density, where the geometry of space-time is perfectly Euclideanly flat. In a flat universe, parallel lines remain parallel forever. The expansion would gradually slow down, coasting towards a stop, but never quite reaching it. This flat geometry is the knife's edge, the tipping point between eternal expansion and eventual collapse. For decades, astronomers tried to measure the cosmic density, adding up all the stars, gas dust and dark matter they could find to determine our ultimate fate. The results, as they grew more and more precise, were astonishing. Our universe is not just close to flat, it is extraordinarily, exquisitely, unbelievably flat. The cosmic density parameter omega, which would be exactly 1 in a perfectly flat universe, is measured today to be 1 to within a fraction of a percent. This observation on its own is a marvel, but when you rewind the cosmic clock, it transforms from a marvel into a statistical impossibility. The state of perfect flatness is a profoundly unstable equilibrium point. It's like trying to balance a sharpened pencil on its very tip. Any tiny deviation from perfect balance at the beginning will be wildly amplified over time. If the early universe had been just a minuscule fraction denser than the critical value, it would have recollapsed into a singularity billions of years ago, long before stars, galaxies, or life could have ever formed. If it had been just a tiny fraction less dense, it would have expanded so violently and so rapidly that gravity would have been too weak to pull matter together. The cosmos would be a thin, featureless soup of isolated particles with no structure, no galaxies, no us. For our universe to be so remarkably flat today, After 13.8 billion years of expansion, it means that at 1 second, after the Big Bang, its density had to be tuned to the critical value to an accuracy of 1 part in a quadrillion. That's a 1 followed by 15 zeros. At the even earlier Planck time, the earliest moment our physics can describe the fine-tuning required is even more absurd equivalent to measuring the distance from one side of the observable universe to the other and being accurate to within the width of a single human hair. The standard Big Bang model offers no reason for this extraordinary initial condition. It simply assumes it. We are asked to accept that our existence hinges on a cosmic balancing act of incomprehensible precision, a value set at the dawn of time with no underlying physical cause. This became known as the flatness problem, another miracle we were forced to accept on faith, another clue that our elegant theory was missing a powerful fundamental mechanism. The final ghost haunting the standard model emerged not from the grand scale of cosmology, but from the esoteric world of particle physics. During the 1970s, physicists were making enormous strides in understanding the fundamental forces of nature. They developed what is known as the standard model of particle physics, a theory of breathtaking success. But their ambition was even greater. They dreamed of a grand unified theory, or GUT, a single elegant framework that would unite the electromagnetic weak and strong nuclear forces into one primordial superforce. These theories predict that at the colossal energies and temperatures present in the first fractions of a second after the Big Bang, these three forces were indeed unified. As the universe expanded and cooled, this unity would have shattered in a series of phase transitions much like water freezing into ice. And just as imperfections like cracks or crystal dislocations can form when water freezes, these guts predicted that the cosmic phase transitions would have inevitably created defects in the fabric of space-time. These defects would manifest as stable, massive elementary particles. The most robust prediction was for the creation of magnetic monopolies, particles with only a single magnetic pole, a north without a south or a south without a north. According to the calculations, these monopoles should have been produced in colossal numbers in the primordial furnace. They would be incredibly massive, thousands of trillions of times heavier than a proton, and crucially they would be stable. Once created, they would last forever. So the theory made a clear prediction: the universe should be absolutely teeming with magnetic monopoles. They should be everywhere. Their immense collective mass would dominate the cosmos, contributing so much gravity that the universe would look vastly different from the one we observe. Yet despite decades of dedicated and ingenious searches in deep-sea mud, in moon rocks, in cosmic rays, with massive detectors built for the sole purpose of catching just one, we have never found a single solitary magnetic monopole. They are completely, utterly absent. This glaring contradiction between the predictions of our most advanced particle theories and the cold, hard reality of astronomical observation was the monopole problem. It was a direct conflict between our understanding of the very large and the very small, suggesting that either our theories of grand unification were wrong, or something profound and unknown had happened in the infant universe to get rid of these unwanted relics. By the end of the 1970s, the situation had become critical. The Big Bang was still the only game in town. Its key successes, the expansion of the universe, the cosmic microwave background, the abundance of light elements, undeniable. But it was a theory that rested on a foundation of seemingly miraculous fine-tuning. It required us to believe that the universe began with its temperature perfectly uniform across causally disconnected regions. It demanded an initial density so precisely balanced on a gravitational knife's edge that it defied all probability. And it could not explain the ghostly absence of the exotic particles our best theories predicted. These were not minor details to be swept under the rug. They were fundamental existential puzzles that pointed to a deep incompleteness in our knowledge. Cosmology had reached a precipice. The standard model was a beautiful, powerful, and celebrated theory that was by all accounts fundamentally broken. What was needed was not a small adjustment, but a revolution. A new idea, a radical addition to the story of our beginning, that could in a single brilliant stroke solve all three cosmic conundrums at once. The stage was set for a flash of insight that would forever change our picture of the universe's first, most violent and most important moment. And so by the dawn of the 1970s, cosmology had reached a strange and disquieting plateau. The resounding success of the Big Bang theory was itself becoming a source of deep intellectual anxiety. It was like possessing a magnificent ancient map that accurately described the contours of every known continent, yet offered no explanation for how those continents came to be, or why their coastlines seemed to fit together with impossible precision. The theory worked beautifully from a few minutes after creation onward, but that infinitesimal sliver of time at the very beginning remained a fortress of paradox, a region of pure mystery that stubbornly resisted every theoretical assault. For the brilliant minds wrestling with these questions, the universe was beginning to feel less like a product of elegant, understandable laws, and more like a cosmic conspiracy, a set-up job of impossible coincidences. The most glaring of these conspiracies was the horizon problem, a riddle whispered by the cosmic microwave background itself. That faint, persistent glow, the afterheat of creation, was a photograph of the infant universe, and it was maddeningly impossibly uniform. Across the entire observable cosmos from one edge of the sky to the very opposite, the temperature of this ancient light varies by less than 1 part in 100,000. Imagine 2 isolated islands separated by an ocean so vast that a message sent from one at the dawn of time could not possibly have reached the other, even by today. Yet when we finally observe them, we find they speak the same language, share the same culture, and their thermostats are set to the exact same degree. This is the absurdity the Big Bang presented. These regions of space, which in the early universe were causally disconnected, light simply had not had enough time to travel between them, had somehow coordinated their properties with breathtaking accuracy. It was a flagrant violation of one of physics' most sacred tenets, the law of locality, the principle that an event in one place cannot instantaneously affect another far away. Information, like everything else, is bound by the universal speed limit of light. For these distant patches of the early cosmos to have settled on the same temperature, they must have communicated, exchanged energy, and reached a thermal equilibrium. But according to the standard Big Bang model's own timeline, they were cosmic strangers. They had never been in contact. The model provided no mechanism, no primordial town crier, no ancient signal that could have traversed the embryonic universe to enforce this uniformity. Physicists would sketch out the light cones, the expanding bubbles of causal influence from these opposite points in the early universe. The circles would grow and grow through cosmic time, but at the moment the microwave background was imprinted, they remained hopelessly separate. There was no overlap, no contact, no explanation. The universe had apparently agreed upon its thermostat settings before the meeting had even been called to order. This wasn't just a puzzle. It was a deep crack in the logical foundation of our cosmic history, a ghost of a causality haunting our most successful theory. The CMB map, once a triumphant confirmation of the Big Bang, was now a celestial taunt, a portrait of an impossible consensus. If the horizon problem suggested a breakdown of the logic, the flatness problem pointed to something even more disturbing, a universe balanced on a knife's edge with a stability that defied all probability. We now know that the geometry of our universe is to the limits of our measurement perfectly flat. On the grandest scales, parallel lines remain parallel, and the angles of a cosmic triangle add up to 180 degrees, just as you learned in school. But in the context of general relativity, this flatness is a precarious, unstable state. The geometry of space-time is determined by the total amount of matter and energy within it, a value cosmologists call the critical density. If the universe began with even a sliver more than this critical density, gravity would have overwhelmed its expansion, pulling everything back together in a catastrophic big crunch billions of years ago. Conversely, if it had begun with a sliver less, the expansion would have been so ferocious, so runaway, that matter would have flung apart too quickly for gravity to ever pull it together. Stars would never have formed. Galaxies would never have ignited. The cosmos would be a thin, cold, and utterly dead void. Our existence is therefore a testament to the fact that the universe began with its density tuned to the critical value with an absurd degree of precision. It is not merely close, it is exact to an astonishing number of decimal places. To appreciate the sheer improbability of this, imagine trying to balance a sharpened pencil on its point. Now imagine that pencil has been balancing not for a few seconds, but for 13.8 billion years. Any tiny nudge, any infinitesimal deviation from perfect balance at the beginning would have been catastrophically amplified over the eons. The gravitational landscape of the universe is a steep mountain peak, and flatness is the tiny singular summit. The standard Big Bang model simply placed the universe at this summit at time zero without any explanation. It was an initial condition that had to be put in by hand, a cosmic fine-tuning so extreme it felt like cheating. Physicists ran the equations backward in time closer and closer to the singularity. With every step they took toward the beginning, the required precision grew exponentially, becoming a tower of infinities. To have the flat universe we see today, the density of the universe at 1 second, after the Big Bang had to be tuned to the critical value to an accuracy of 1 part in a quadrillion. At the Planck time, an instant so early it defies our current physics, the required tuning becomes so ludicrously fine it is difficult to even write down the number. This was not a situation that scientists could accept with a shrug. Science seeks to explain why things are the way they are through underlying principles, not to simply state that we won the cosmic lottery, against odds that make winning every real-world lottery simultaneously for 1,000 years seem like a dead certainty. The flatness of the universe under the old model looked less like a law of nature and more like a miracle. It screamed of a missing ingredient, a powerful physical process in the universe's earliest moments that had not just placed the pencil on its tip, but had actively, dynamically forced it to stay there, ironing out any curvature and driving the cosmic density toward this one special life-permitting value. But what could that process possibly be? The standard model was silent. It offered only the brute fact of our unlikely existence, a fact that sat uncomfortably close to philosophical arguments for divine intervention, a place where empirical science could not and would not go. The community was in a state of intellectual gridlock, staring at 2 fundamental properties of our cosmos, its uniformity and its flatness, and possessing a theory that could only explain them by declaring them to be exquisitely, inexplicably fortunate accidents. While cosmologists were staring out at the heavens in frustration, another group of scientists was peering inward into the subatomic realm with an ambition that was just as grand. During the 1970s, particle physicists were celebrating their own monumental achievement, the Standard Model of particle physics. This powerful framework described 3 of the 4 fundamental forces of nature: the strong nuclear force that binds atomic nuclei, the weak nuclear force that governs radioactive decay, and electromagnetism with stunning success. Gravity for the moment remained the odd one out, yet as powerful as the Standard Model was, it felt incomplete. It described 3 separate forces with 3 different strengths, and a menagerie of seemingly arbitrary particles. To physicists like Sheldon Glashow Abdussalam and Steven Weinberg, who had unified the weak and electromagnetic forces into a single electroweak theory, this was not the final word. They dreamed of a deeper unity, a simpler, more elegant reality that existed at energies far beyond what any particle accelerator on Earth could ever hope to achieve. They were searching for a grand unified theory, or gut. The central idea of guts was as simple as it was profound. As you turn up the energy, as you rewind the cosmic clock back to the inferno of the first instance of creation, the distinctions between the fundamental forces begin to dissolve. The theories predicted that at an unimaginable temperature of 10 quadrillion degrees, the strong, weak, and electromagnetic forces would merge. Their individual identities would melt away, unifying into a single primordial superforce. In this state, the universe would have been a place of profound symmetry and simplicity. The babel of different forces and particles we see today would have been speaking a single unified language. Then, as the universe expanded and cooled in the first fraction of a second, this perfect symmetry would have broken. Like steam condensing into water and then freezing into ice, the superforce would have frozen out into the separate, distinct forces we now observe. The different phases of water are all H2O, but they behave in radically different ways. So too, the gut theorists proposed are the forces of nature merely different phases of a single underlying reality. This was a breathtakingly beautiful idea. It promised to simplify our understanding of physics, to reveal a hidden order beneath the apparent complexity of the cosmos. For cosmologists, it was even more tantalizing. For the first time, a concrete theory from particle physics was offering a detailed picture of the universe during the very moments that had been a complete blank slate. The gut era, that fleeting instant when the superforce reigned, occurred precisely within the mysterious gap in time where the solutions to the horizon and flatness problems had to lie. A wave of optimism swept through the community. Perhaps the physics of grand unification, the very process of these forces splitting apart, would naturally produce a flat and uniform universe. Maybe the symmetry breaking itself was the missing mechanism. The two frontiers of physics, the study of the immensely large and the infinitesimally small, were converging on the same moment of creation. It felt like the dawn of a true theory of everything, a final blueprint for reality. The solution seemed tantalizingly close hidden within the elegant mathematics of these new and powerful theories. But this grand synthesis, this beautiful convergence of cosmology and particle physics, would not bring clarity. Instead, it would conjure a monster. Grand unified theories, for all their elegance, came with a terrifying prediction, a piece of unwanted baggage that threatened to destroy the entire framework. They predicted the existence of a new bizarre type of particle, the magnetic monopole. We are all familiar with magnets having two poles, a north and a south. If you cut a bar magnet in half, you do not get a separate north pole and a south pole. You get two smaller magnets each with its own north and south. A magnetic monopole would be a particle that was a pure north or a pure south pole all by itself, an isolated magnetic charge, the magnetic equivalent of a single electron. No one had ever definitively detected one, but Guts predicted that they should have been created in colossal numbers during the very symmetry-breaking event that separated the strong force from the electro-weak force. The logic was inescapable. As the primordial universe cooled and the unified superforce shattered, this process would not have been perfectly smooth across the entire cosmos. It would have happened in different ways in different regions, like ice crystals forming in a freezing lake. At the boundaries where these different regions met, defects would have been trapped in the fabric of space-time topological defects like snags in a sweater. And these defects, according to the Gut equations, were the magnetic monopoles. The theory didn't just predict a few, it predicted a cataclysmic flood. For every few thousand protons and neutrons, there should have been at least one magnetic monopole. The problem was that these were not predicted to be lightweight ephemeral particles. The theory suggested they would be stupendously massive, trillions of times heavier than a proton each one, a tiny primordial black hole of concentrated energy. If they existed in the predicted numbers, they would have been the dominant form of mass in the universe by an overwhelming margin. The cosmos would not be filled with galaxies, stars and planets, but with a cold, dark sea of supermassive magnetic monopoles. The gravitational pull of this monopole deluge would have been so immense that it would have halted cosmic expansion and caused the universe to recollapse into a singularity when it was barely a few thousand years old. Our 13.8 billion-year-old universe filled with sparkling galaxies simply should not exist. The very fact that we are here to ask the question is the most powerful evidence that this prediction is catastrophically wrong. Experimental physicists like Blas Cabrera at Stanford set up ingenious experiments to search for them, hoping to catch a single monopole drifting through their detectors. The silence from these experiments was deafening. The monopoles were not there. This was a crisis of the first order. The most promising idea to explain the physics of the early universe, grand unified theory, had made a bold, clear and unavoidable prediction that was spectacularly contradicted by observation. It was as if a brilliant theory of meteorology predicted that the sky should be filled with giant flying elephants, and a simple glance out the window proved it false. The beautiful symphony of grand unification had produced a cacophonous, universe-destroying roar. By the end of the 1970s, the mood had soured. Cosmology was trapped in a theoretical cul-de-sac. The standard Big Bang model was haunted by the ghosts of fine-tuning and a causality in the flatness and horizon problems. The leading candidate to fix it, grand unified theory, had created a new, even more deadly paradox in the monopole problem. The field was stuck. The evidence from the cosmos was screaming that a fundamental piece of the puzzle was missing. The very beginning of time was not just a mystery, it was an arena of contradictions, a place where our best theories went to die. A revolution was needed, but from where would it come? The community was staring into an abyss of ignorance, waiting for a flash of insight for a new story that could somehow reconcile the impossible smoothness, the improbable flatness, and the terrifying absence of the monsters that should have been. And so by the twilight of the 1970s, cosmology had arrived at a profound and troubling impasse. We had constructed a magnificent history of our universe, the Big Bang Theory, yet it stood upon a foundation riddled with inexplicable coincidences. These three great cosmic riddles, the horizon, the flatness, and the monopole problems we've just explored, were not minor inconsistencies. They were deep structural cracks in our understanding of everything, suggesting that a fundamental chapter of our origin story was not just incomplete but entirely missing. The universe we saw simply should not exist. It was too uniform, too balanced, too empty of predicted relics. Science needed a hero, a new idea so powerful it could mend the fabric of our creation story. But that idea wouldn't come from a grand coordinated search. It would arrive as the greatest breakthroughs so often do not with a thunderclap, but as a whisper, in the mind of a single physicist working late into the night on a problem he believed had nothing to do with the birth of the universe itself. That physicist was Alan Guth, a young particle theorist at Cornell University. His focus in 1979 wasn't on the grand architecture of the cosmos, but on its most elementary subatomic components. He was immersed in the exotic world of grand unified theories, or GUTS, the ambitious attempt to unite three of nature's fundamental forces into a single elegant framework that would have existed in the extreme heat of the early universe. Within these theories lay a strange and fascinating concept, the idea of a false vacuum. It's a state of pure energetic nothingness, but a deeply unstable one. Think of it like a vast expanse of water vapour, perfectly pure, that has been cooled far below its freezing point yet has somehow failed to turn into ice. It exists in a precarious supercooled state, holding an immense amount of latent energy ready to unleash it in a sudden violent phase transition the moment it is disturbed. Guth was exploring how the universe might have navigated this transition from an unstable high-energy false vacuum to the stable low-energy true vacuum we inhabit today. He was not trying to solve the riddles of cosmology. He was just following the logic of his equations. On a cold December night, hunched over his notes, something extraordinary began to emerge from the mathematics. The equations describing this phase transition, this cosmic freezing, were behaving in a way no one had anticipated. According to his calculations, the energy locked within that false vacuum would have a unique and astonishing property: it would generate a repulsive gravitational force. It was a form of anti-gravity, not pushing matter apart, but pushing space itself apart. The energy of empty space, he realized, could act as a colossal engine, driving a runaway exponential expansion. This wasn't the steady decelerating expansion of the standard Big Bang model. This was something else entirely. It was a cosmic accelerator pedal slammed to the floor. In a sudden, electrifying flash of insight, Guth saw the connection. This wasn't just an obscure process in particle physics. This could be the missing event, the lost chapter at the very beginning of time. He grabbed his notebook and in a flurry of excitement scribbled the words that would change cosmology forever: spectacular realization. He had stumbled almost by accident upon the secret engine of creation. He had discovered cosmic inflation. What Guth had just envisioned was a moment of unimaginable violence and velocity occurring in the first whisper of existence around 10 to the power of minus 36 seconds after the Big Bang. At this instant, the universe was dominated by the bizarre physics of the false vacuum, a state governed by a new hypothetical energy field that we now call the inflaton field. This field permeated all of space, and its immense energy density created a gravitational repulsion that was staggering in its power. It seized the nascent fabric of space-time and stretched it with a ferocity that defies all earthly comparison. During this period, the universe didn't just expand. It doubled in size and then doubled again and again and again in an exponential cascade of creation. It's a timescale so short that our minds struggle to grasp it. Yet in that sliver of a moment, the universe is thought to have doubled in size at least 100 times over, swelling from a volume far smaller than a single proton to something larger than a grapefruit. This hyper-expansion, this celestial blowtorch that reforged the cosmos in its opening act, was inflation. And as Guth began to explore its consequences, he realized with growing astonishment that this single, ferocious event didn't just fit into the Big Bang theory. It fixed it. It was the master key that unlocked all three of cosmology's intractable puzzles. First, consider the horizon problem, that maddening mystery of the universe's impossible uniformity. How could regions of the cosmos separated today by billions of light-years of impassable distance share the exact same temperature as if they had once been in intimate contact? The standard Big Bang offered no answer, but with inflation the solution becomes breathtakingly elegant. The theory proposes that before the inflationary burst began, the entire region, destined to become our observable universe, was microscopic, far, far smaller than we had ever imagined. It was a subatomic patch of space so minuscule that it was in fact causally connected. Every point within that primordial speck had ample time to interact to exchange heat and to settle into a state of perfect thermal equilibrium, a uniform temperature throughout. It was a tiny, smooth, homogeneous broth. Then inflation switched on. This microscopic uniform region was seized by the inflaton field and stretched, magnified and expanded at an exponential rate. Imagine taking a single perfectly coloured pixel on a computer screen and blowing it up until it fills not just your screen but the entire stadium you're sitting in. The colour would be perfectly uniform from one end to the other, not because distant points miraculously coordinated, but because they were all originally part of the same single uniform pixel. Inflation did precisely this to the fabric of reality. The uniformity we see in the cosmic microwave background isn't a miracle. It's the genetic echo of a shared microscopic ancestry, a family resemblance stretched across the entire sky. The universe isn't uniform by coincidence. It is uniform because all the vast disparate regions we see today are in reality magnified fragments of a single tiny interconnected neighbourhood from the dawn of time. Next, Guth turned his attention to the flatness problem, the universe's improbable architectural balancing act. Why is the geometry of space-time so exquisitely flat poised on the razor's edge between a closed sphere that would collapse and an open saddle that would fly apart? Any deviation from perfect flatness in the early universe should have been wildly amplified over 13.8 billion years, yet we find ourselves in a universe that is against all odds geometrically perfect. Inflation provided the answer with an equally stunning simplicity. The mechanism that stretched space to solve the horizon problem would also inevitably flatten it. Think of the surface of a tiny crumpled and highly curved balloon. If you were an ant living on it, you could easily perceive its curvature. But now imagine inflating that balloon to the size of the Earth. For you, the tiny ant, the surface you stand on would appear perfectly flat in every direction you look. You would have to travel thousands of miles to detect any hint of the globe's underlying curvature. Inflation was this process on a cosmic scale. Whatever the initial curvature of the universe might have been curled up wrinkled complex, the sheer, overwhelming force of the inflationary expansion would have stretched it out, smoothing every wrinkle, flattening every curve, ironing the very fabric of space-time into a state of near-perfect flatness. The immense scale of our observable universe is just a tiny patch on this unimaginably larger inflated cosmos, so it naturally appears flat to us. Once again, what seemed like an absurd fine-tuning was in fact an unavoidable consequence. The universe isn't flat because it was born lucky. It's flat because inflation was the ultimate cosmic steamroller, leaving behind a smooth and predictable terrain. Finally, there was the monopole problem, the puzzle of the missing monsters. The very same grand-unified theories that had led Guth to the concept of the false vacuum also predicted that the early universe should have been flooded with exotic, super-heavy particles called magnetic monopoles, particles with only a north or south pole but not both. They should have been created in abundance during the universe's initial phase transitions, like defects forming in ice as water freezes. If the theories were correct, these monopoles should be everywhere, their immense mass dominating the cosmos. Yet we have never ever found one. Our universe is mysteriously clean. Inflation offered a brilliant and compelling explanation for their absence. Yes, the monopoles were likely created just as the theories predicted in that first fiery moment. but they were created before the inflationary burst began. In that pre-inflationary micro-universe, they might have been relatively common. Then the inflaton field ignited and the space between these particles began to expand exponentially. The same process that stretched the universe flat and uniform also diluted its contents with ruthless efficiency. Imagine placing a single drop of ink into a glass of water. Now, if that glass of water suddenly expanded to the size of the Pacific Ocean, what are the chances you would ever find a single molecule of that ink again? They would be infinitesimally small. Inflation did this to the magnetic monopoles. It expanded the volume of space so profoundly, so overwhelmingly, that the density of monopoles dropped to virtually zero. There might be one monopole in our entire observable universe, or there might be none. They aren't gone. They have simply been spread so far apart by that ancient explosive expansion that we are statistically guaranteed never to encounter one. They are the lost relics of a forgotten age diluted into cosmic oblivion. In one spectacular stroke, a single idea born from a late-night calculation in an unrelated field had solved the three greatest paradoxes of our cosmic origin. It was a stunning intellectual achievement, a moment when the murky, confusing picture of the early universe snapped into sharp, brilliant focus. Inflation wasn't just an add-on, or a patch to the Big Bang theory. It was a prequel, a foundational pillar that explained why the conditions for the Big Bang were what they were. It provided a coherent, compelling, and physically motivated mechanism that transformed a series of baffling coincidences into a set of predictable and necessary outcomes. The idea was radical, proposing a new field and a new form of energy unlike anything we have ever directly experienced. It described a moment of creation more violent and more extreme than anything previously conceived, but its explanatory power was undeniable. It felt right. It felt true. It provided the universe with a plausible infancy, a history that led directly to the cosmos we inhabit today. Yet this very success immediately raised a new, and perhaps even more profound question. If inflation created a universe that was perfectly smooth, perfectly flat, and perfectly uniform, then where did we come from? Where did the galaxies, the stars, the planets, and the intricate cosmic web of structures arise? In ironing out all the old problems, inflation seemed to have created a new one, a universe too perfect, too simple to account for the rich complexity all around us. The story was not over. In fact, the greatest secret of inflation, its power not just to smooth the universe, but also to plant the seeds of its future glory, was still waiting to be revealed. And for a breathtaking moment, it seemed the puzzle was solved. The fury of that first fraction of a second, the inflationary inferno had smoothed the cosmos, flattened its geometry, and connected its most distant shores. The theory was a masterpiece of cosmic architecture, a single elegant pillar supporting the entire observable universe. It was a moment of pure, unadulterated triumph in the history of human thought. But within this perfect solution, a deep and terrifying flaw was lurking a ghost in the sublime machine of creation. Alan Guth's initial model, for all its revolutionary genius, had built the most magnificent engine imaginable, but he had forgotten one crucial component: the brakes. His equations described how to turn inflation on with spectacular success, but they offered no clean way to turn it off. The universe, according to his original calculations, would become trapped in its own explosive growth. It was a process called a phase transition, much like water freezing into ice. As the inflationary energy field decayed, it was supposed to convert its vast potential energy into the hot, dense soup of particles that would become our Big Bang. Instead, Guth's model predicted this transition would happen in isolated pockets, creating separate bubbles of new reality within the still inflating vacuum. These bubbles would indeed form, but the space between them would continue to expand at that incomprehensible, exponential rate. The bubbles would be driven apart from one another so violently, so instantly, that they could never meet, never coalesce, never merge to form one large uniform universe like the one we inhabit. Our cosmos would be a broken thing, a chaotic mess of isolated, empty voids and fiery patches of matter, a failed creation story where the heavens remained forever divided. The universe would be cold, lumpy, and fundamentally inhomogeneous, the very problems inflation was invented to solve. It was a fatal paradox. The cure, it seemed, was worse than the disease. For the scientific community, this was more than a setback. It was a crisis of logic. The theory was too beautiful, too powerful in its explanations to be completely wrong. Yet this graceful exit problem, as it came to be known, was an intractable barrier. How did the cosmos step off the inflationary accelerator and gently coast into the more sedate expansion we see today? How did that single unified bubble bubble come to dominate, reheating itself evenly into the primordial fireball of the Big Bang? The universe needed a smoother, more controlled descent from its energetic peak. The switch that flipped creation into high gear needed a dimmer, not a hard-off. The search was on for a mechanism, a refinement that could salvage this brilliant idea from its own self-destructive mathematics. The answer, when it came, would not only solve the graceful exit problem, but would also unlock a vision of reality so vast, so strange, that it would dwarf everything we'd ever conceived of as the universe. The breakthrough came not from one mind, but from a convergence of insights. In Russia, a young physicist named Andrei Linde was wrestling with the same conundrum. He envisioned the inflationary energy field, this inflaton field, not as a system falling precariously off a cliff, but as something rolling gently down a long, shallow hill. In America, physicists Andreas Albrecht and Paul Steinhardt arrived at a nearly identical picture. Together they developed what became known as new inflation, and later Linde's more robust chaotic inflation. In these models, the end of inflation wasn't a sudden violent shattering like ice, forming in disjointed crystals. It was a slow, graceful process, a cosmic exhalation. Imagine a vast undulating landscape of potential energy existing before space and time as we know them. In this landscape, the inflaton field is like a ball placed randomly at some high elevation. In Guth's original model, the ball was trapped in a small dip at the top of a high plateau, needing to quantum tunnel through a barrier to fall off a process that would happen randomly and create those disconnected bubbles. But in the new models, the landscape was different. It was a gentle sweeping slope, a slow roll potential. The ball representing the energy state of the nascent universe didn't have to tunnel through anything, it simply began to roll. And as it rolled, it drove the exponential expansion of space. This rolling was inflation. The beauty of this picture was its ending. As the ball rolled further down the slope, the hill became steeper. It picked up speed, and when it finally reached the bottom of the valley, the potential energy it had carried was released all at once in a brilliant flash of light and heat. The rolling stopped, the engine cut out. And that single coordinated release of energy happening everywhere throughout our cosmic patch was the reheating, the true moment of the hot Big Bang. It was a smooth, controlled and global transition. The entire universe we can see, and everything far beyond our horizon, was born from a single continuous rolling event, ensuring it would be uniform and connected. The graceful exit problem was solved. The theory was saved. And in that moment of salvation, scientists unknowingly opened a door onto infinity. Because the solution held within it a staggering, almost terrifying implication. Linde in particular pushed the logic to its ultimate conclusion. He realized that in this new picture, inflation might not have to end everywhere at the same time. His model of chaotic inflation began with a premise of utter randomness. Imagine that pre-inflationary state not as a single ball on a hill, but as a vast turbulent sea of energy, a quantum foam where the inflaton field has different values at every single point. In some regions, the value might be low down in the valley. In those places, inflation never starts and they may simply collapse or remain inert. But in other regions, by pure chance, the inflaton field would have an incredibly high value, placing it high up on that energy slope. In those regions, the ball would begin to roll and inflation would begin. And here is the crucial insight, the one that changes everything. While the inflaton field is slowly rolling downhill in one region, creating a universe like ours, the very nature of quantum mechanics insists that the field is also subject to random fluctuations. It jiggles. Most of these quantum jiggles are tiny, insignificant tremors. But in a system as powerful as cosmic inflation, even a small upward jiggle can have monumental consequences. Occasionally, a quantum fluctuation will be large enough to push the inflaton field back up the hill in some distant patch of space. This means that while inflation is ending in our region, creating our universe, The quantum leap has kicked another far-flung region back into a state of high energy, resetting the inflationary clock. That region will then begin its own exponential expansion, spawning its own universe. And within that new expanding region, the same process will repeat. Quantum fluctuations will inevitably kick some of its subregions back up the hill, igniting yet more inflation, which will spawn yet more universes. The process once started appears to have no end. Inflation stops in one place, only to rage even more fiercely in another. It's a cosmic chain reaction, a fire that never goes out, constantly creating new embers that drift away to start new fires. Linda called this process eternal inflation. The consequence is as profound as it is dizzying. It suggests that our Big Bang was not the beginning. It was just a beginning. Our universe, our entire observable cosmos, is but one bubble, one pocket universe that happened to cool down in a vast, ever-expanding, ever-inflating meta-universe. A multiverse. This isn't the multiverse of science fiction, a realm of parallel timelines and alternate choices. This is a physical cosmological multiverse born from the same equations that so beautifully describe our own origins. It is a foaming, bubbling sea of creation where new universes are born from the fabric of inflating space-time every single moment. Imagine a pot of boiling water. Our universe is like a single bubble of steam that rises, expands, and cools. But the water itself, the underlying inflationary medium, continues to boil for eternity, endlessly producing more bubbles. Each bubble is a universe, and the space between them is the eternally inflating parent vacuum expanding so rapidly that the bubbles once formed can never interact. They are causally disconnected island realities in an infinite cosmic ocean. This vision of reality forces us to confront the deepest questions of our existence. What would these other universes be like? The answer from the theory is both simple and mind-bending. They would be different. The valley at the bottom of the potential energy landscape that our inflaton field rolled into determines the fundamental laws of physics in our universe. It sets the masses of particles, the strengths of forces, the very character of our reality. But in a complex energy landscape, there could be countless other valleys, other stable states, each corresponding to a different set of physical laws. In one universe, gravity might be 1,000 times stronger, collapsing everything into black holes before stars could even form. In another, the electromagnetic force could be weaker, preventing atoms from ever binding together, resulting in a thin, lifeless soup of elementary particles. Some universes might be stillborn flashes of existence that last for a mere microsecond. Others might be stable but utterly alien, governed by forces and populated by particles we can't even imagine. They would be universes of pure light, or universes of crystalline structures spanning galaxies, or universes with dimensions of space we could never perceive. Our existence in this grander picture begins to look less like a miraculous, finely tuned event and more like a statistical inevitability. With an infinite number of universes being generated, each with a random roll of the cosmological dice, it is almost guaranteed that some of them, by pure chance, would have the right combination of physical laws to allow for complexity, for chemistry, for stars, planets, and life. We find ourselves in a universe that appears perfectly designed for us, because we could not have evolved in any of the others. This is the anthropic principle on a cosmic scale. We are not the central players in a single cosmic drama, but rather the inhabitants of one lucky bubble in an incomprehensibly vast ensemble of possibilities. It's the final step in the Copernican revolution. Not only is our planet not the centre of the solar system, and our sun not the centre of the galaxy, but our entire universe may not even be the sole reality. It might just be one entry in an infinite cosmic catalogue. This idea, of course, ignited furious debate. To some, it was the logical, beautiful, and unavoidable endpoint of our most successful cosmological theory. It explains the apparent fine-tuning of our universe without resorting to a supernatural designer. It is a natural consequence of combining quantum mechanics and general relativity in the earliest moments of time. To others, it felt like a betrayal of the scientific method. How can you test a theory that posits the existence of other universes that are by their very definition causally disconnected from our own? We can never visit them, never see them, never receive a single photon of light from their shores. Does a theory that makes untestable predictions even qualify as science? Or has it crossed the line into metaphysics and philosophy? Where does the boundary lie between a cosmological model and a creation myth? The concept of eternal inflation divided the physics community, pushing scientists to the very edge of what can be known, forcing them to question the nature of evidence itself. The theory of inflation, born from a desire to explain the simple, elegant smoothness of our own sky, had led us to this vertiginous precipice. It left us staring into an abyss of infinite possibilities, questioning the uniqueness of our own existence. It presented us with a vision of a cosmos more grand, more strange, and more humbling than anyone had ever dared to imagine. And it posed the ultimate challenge. If this eternal multiverse-spawning inflation is real, if it truly is the process that gave birth to our world, it could not have been a perfectly silent event. The same quantum fluctuations that ensure inflation becomes eternal would have also been imprinted on the fabric of our own space-time. They would have shaken the nascent universe, sending out ripples not of light, but of gravity itself. These primordial gravitational waves, a faint ghostly echo of that first explosive instant, would be the smoking gun. They would be the only possible messengers from that era, the only physical proof we could ever hope to find. The search for these waves would become the modern grail of cosmology, a quest to find the whisper of creation, and perhaps confirm that we are but one voice in an infinite cosmic choir. And so the theory stood a breathtakingly elegant solution, a cosmic origin story of unparalleled power and simplicity. It was a mathematical cathedral constructed in the minds of theorists to solve the universe's most vexing paradoxes. But for all its intellectual beauty, inflation remained a ghost in the machine of cosmology, a brilliant conjecture without a body of proof. Science, after all, is not a faith, it is a discipline of evidence. A theory, no matter how compelling, must eventually leave the pristine world of equations and face the cold, hard judgment of observation. It must make a prediction so specific, so audacious, that finding it would be unmistakable, and failing to find it would be fatal. For cosmic inflation, that day of judgment was coming. The courtroom was already prepared, waiting for us since the dawn of time. Its name was the cosmic microwave background. This is the universe's baby picture, the most ancient light we can ever hope to see, a faint ghostly hum of microwaves emanating from every direction in the sky. It is the afterglow of the Big Bang itself, a wall of light released when the cosmos was a mere 380,000 years old, as it cooled enough for atoms to form and photons to finally travel free. For decades we had seen this light as astonishingly, impossibly uniform. A perfect thermal bath at 2.7 degrees above absolute zero no matter where we looked. This very uniformity was one of the puzzles inflation was built to solve. But hidden within that theory was a far more subtle and profound prediction. The engine of inflation, the quantum field that drove that hyper-expansion, was not perfectly smooth. Like any quantum system, it fizzed and crackled with fleeting microscopic fluctuations, tiny ephemeral jitters in the energy of space-time itself. Inflation proposed that as the universe swelled by an unimaginable factor, these minuscule quantum ripples were stretched along with it. They were magnified from subatomic nothings into gargantuan waves of energy and density spanning millions of light years. These waves, this primordial texture, would have been imprinted upon the fabric of the cosmos. Some regions would be infinitesimally denser, infinitesimally hotter, others infinitesimally less dense, infinitesimally cooler. The theory predicted that these tiny variations, these seeds of structure, should be forever frozen into that fossil light of the cosmic microwave background. The challenge, a monumental one, was to see them. The predicted fluctuations were so faint, so subtle, they amounted to temperature differences of just 1 part in 100,000. It was like trying to find a ripple just a few centimeters high on an ocean the size of the Earth. Many believed it was a fool's errand, an impossible task, but humanity is defined by its pursuit of the impossible. In 1989, NASA launched the Cosmic Background Explorer, or COBE. It was a vessel designed for a single noble purpose: to stare into the dawn of time and take its temperature with unprecedented precision. For years it orbited the Earth shielded from the sun, its instruments cooled to near absolute zero, soaking in the faint whispers of creation. The team of scientists on the ground waited, processing terabytes of data. meticulously filtering out the noise from our own galaxy, from our solar system, from the instrument itself. They were sifting through a cosmic haystack for a single extraordinary needle. They were searching for the fingerprint of our own origin. What they found would change cosmology forever. In 1992, the results were unveiled to a waiting world. The map they produced was at first glance a simple oval, mottled with faint patches of blue and red. It looked unimpressive, like a poorly tuned television screen. But what it represented was a staggering triumph. The blue spots were the colder, slightly less dense regions. The red spots were the hotter, slightly denser ones. These were the primordial fluctuations. These were the seeds of everything. The lead scientist George Smoot famously declared it was like seeing the face of God. He was not being hyperbolic. In those faint smudges, you were witnessing the gravitational blueprint for the entire cosmos. Every vast supercluster of galaxies, every spiraling nebula, every star, every planet, and every one of us owes its existence to these minuscule imperfections magnified by inflation from the quantum realm. It was a monumental discovery, a Nobel Prize-winning achievement that provided the first piece of hard observational evidence for the inflationary epoch. The theory had stepped out of the shadows of speculation and into the light of day. Yet Cobb's vision was blurry, its resolution low. It had proven that the seeds were there, but it couldn't tell us much about their character. Inflation, however, made even more specific predictions about the nature of these fluctuations. It predicted their statistical properties with mathematical certainty. To test this next deeper layer of the theory, we would need a sharper eye. We would need a new explorer, one capable of mapping the infant universe in high definition. That explorer was NASA's Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001. If Cobb provided a rough sketch, WMAP was designed to be the master cartographer. Sent 1 million miles from Earth to the stable gravitational point known as L2, it was free from the thermal and radio interference of our own planet. For 9 years, it patiently scanned the heavens, its twin telescopes charting the ancient sky, with a resolution 45 times greater than Cobb's. What it was searching for were 2 key statistical signatures, 2 golden rules that would be the definitive test of the inflationary model. The first is a property known as scale invariance. Imagine the pattern of fluctuations as a kind of cosmic music, a sound resonating from the Big Bang. Some theories of structure formation might predict a sound dominated by a single note, with large fluctuations on one particular scale but not others. Inflation, however, predicts something much more like white noise or a cosmic hiss. It predicts that the ripples should have nearly the same intensity, the same amplitude across all scales. From the very largest patches on the sky down to the smallest ones, WMAP could resolve the strength of the fluctuation should be almost identical. This scale invariance is a direct consequence of the steady exponential stretching during the inflationary period. It's a powerful and unique prediction. The second golden rule concerns the distribution of the spots themselves. Inflation posits that these structures arose from random, uncorrelated quantum events. Therefore, the pattern of hot and cold spots on the sky should be perfectly random, what mathematicians call a Gaussian distribution. There should be no special patterns, no hidden alignments, no preferred directions. The universe on its largest scales should not have a secret axis or a cosmic North Star. It should be statistically the same everywhere you look. This predicted randomness is a deep reflection of the quantum mechanical origins of all structure. As the data from WMAP poured down to Earth and was meticulously assembled into a new, stunningly detailed map of the CMB, the scientific community held its breath. This was the moment of truth. Would the universe conform to the elegant mathematics of inflation? The answer when it came was an overwhelming, resounding yes. The WMAP data fit the predictions of the simplest inflationary models with breathtaking fidelity. The fluctuations were almost perfectly scale invariant. They were Gaussian to an astonishing degree of precision. It was as if the theorists had been given a glimpse of the universe's answer key decades in advance. The WMAP results transformed cosmology. They allowed us to precisely determine the age of the universe 13.7 billion years. They told us its composition only 5% normal matter, 27% mysterious dark matter, and 68% enigmatic dark energy. and most importantly, they elevated inflation from a compelling idea to the standard foundational paradigm of modern cosmology. The case was becoming overwhelmingly strong, but science never rests. Its core tenet is to keep questioning, to keep refining, to push the boundaries of measurement ever further. UMAP's portrait of the early universe was a masterpiece, but even masterpieces can be improved upon. There were still subtle questions to answer, tiny details in the inflationary model to test. One of the most delicate predictions concerns the nearly scale invariant. While the fluctuations are almost the same on all scales, the simplest models of inflation predict a tiny subtle deviation. Specifically, they predict that the fluctuation should be very slightly stronger on larger scales than on smaller scales. This is known as a spectral tilt, and finding it would be a powerful confirmation of the dynamics of the inflationary field as it slowly rolled towards the end of its expansionary phase. Measuring this tiny tilt required a level of sensitivity and precision that went far beyond even WMAP. This was the mission of the European Space Agency's Planck satellite launched in 2009. Planck was the apotheosis of CMB observation, an instrument of almost absurd power and sophistication. Its detectors were cooled to just 1/10 of a degree above absolute zero, making them the coldest known points in space. This allowed it to map the CMB with a sensitivity so extreme it could detect temperature variations of a few millionths of a degree. Its resolution was so sharp it could see details 3 times smaller than WMAP. Over 4 years, Planck created the most perfect, most detailed image of the infant universe that humanity has ever produced. It is a work of both scientific and artistic genius, a stunning tapestry of creation's first light. And woven into that tapestry was the final proof the community had been waiting for. Planck confirmed the predictions of inflation to a level that silenced almost all remaining doubt. It measured the spectral tilt with pinpoint accuracy, and the value it found was exactly in the range predicted by the leading inflationary models. It confirmed the Gaussian randomness of the fluctuations with statistics that left no room for argument. It mapped the subtle ways that ancient light was bent by intervening galaxies, allowing for an even more precise measurement of the universe's fundamental parameters. Planck's data didn't just support inflation. It began to act as a filter, ruling out more complex exotic versions of the theory and favouring the simplest, most elegant models. The cumulative evidence from COBE to WMAP to Planck presents one of the most triumphant stories in the history of science. A wild speculative idea born from pure theory was tested against the ancient light of creation and was found to be true in every particular. Yet for all this success, there remains one final, elusive prediction. A discovery so profound it is often called the smoking gun of inflation. If it is ever found, it would be the ultimate confirmation, a piece of evidence as direct and unambiguous as a footprint at a crime scene. We have seen the effects of inflation in the density ripples that seeded galaxies, but inflation should have done something more. The violent exponential stretching of spacetime itself, a process of unimaginable energy, should have shaken the very fabric of reality to its core. It should have generated a storm of gravitational waves, primordial ripples in space-time that would have propagated across the cosmos unimpeded ever since. Unlike the density waves that created the hot and cold spots, these gravitational waves would not have clumped matter together. Instead, they would have subtly stretched and squeezed space itself as they passed through the early universe. This stretching and squeezing would leave a unique and extraordinarily faint signature in the light of the cosmic microwave background. It would not be in the temperature of the light, but in its polarization, the orientation of the light waves. The density waves from inflation produce a simple curl-free polarization pattern known as E-modes. But primordial gravitational waves would twist and shear the polarization, creating a faint swirling vortex-like pattern. This specific type of polarized signal is known as a B-mode. Finding these B-modes is the holy grail of modern cosmology. The signal is predicted to be 100 times fainter than the faintest temperature fluctuations we have already measured. It is an echo of an echo, buried deep within the noise of our own galaxy, which also emits polarized microwave light. The search is one of the most technologically demanding endeavours ever undertaken. In 2014, a team of researchers using a telescope at the South Pole, called BICEP-2, announced they had detected just such a signal. The cosmological community was electrified. It seemed the smoking gun had been found. But the careful, self-correcting process of science soon kicked in. Further analysis, including data from the Planck satellite, revealed that much of the signal they had seen was not from the dawn of time but was instead contamination from interstellar dust in our own Milky Way. The initial jubilation turned to sober disappointment but not defeat. It was a powerful lesson in the difficulty of the search and the integrity of the scientific method. The hunt is far from over. A new generation of incredibly sensitive experiments in the high dry deserts of the Chilean Andes and at the desolate expanse of the South Pole are currently scanning the skies. Future space missions are being designed with the express purpose of hunting for this faint, swirling signature. They are listening for the final whispered secret of the Big Bang. Because to find primordial B modes would be to achieve something truly extraordinary. It would be more than just another confirmation of inflation. It would be a direct window into the moment of creation itself. We would be seeing the effect of gravity not as a classical force, but as a quantum phenomenon born from the same quantum field that drove inflation. It would be the first ever observational evidence of quantum gravity. We would be sensing the tremors of spacetime's birth, the gravitational echo of that first incomprehensible fraction of a second when all of existence was forged. The search continues on the frontiers of technology, and at the edge of time for the final definitive proof of the split second that created our universe. And so the grand tapestry of our cosmic history, once a bewildering collection of frayed threads and confounding patterns, resolves into a breathtaking and coherent whole. The baffling clues left at the scene of the crime of creation a universe impossibly flat, a thermal equilibrium that defied the laws of light speed, a perplexing absence of exotic relics that should have been there, all find their resolution not in a series of disconnected explanations, but in one single cataclysmic event. A moment of such ferocious and incomprehensible power, it seems less like physics and more like mythology. This is the ultimate legacy of inflation. It is the master key that unlocks the fundamental architecture of our reality, the single violent exhalation that took a universe of unimaginable density and stretched it into the serene expanse we witness tonight. It answered the how that haunted cosmologists for decades, transforming our origin story from a mystifying singularity into a dynamic physical process. Before we stared at the cosmic microwave background as if it were a beautiful but inscrutable portrait. Now we see it for what it truly is, the fossilized aftermath of that initial hyperexpansion. The near-perfect uniformity across the sky is no longer a paradox but the expected outcome of a shared intimate past, a time when every point in our observable universe was once close enough to touch before being flung apart with unimaginable speed. And the tiny, almost imperceptible temperature fluctuations, those subtle variations of 1 part in 100,000, are no longer just statistical noise. They are the most profound message ever received from the past. For in these gentle ripples we see the ghost of the quantum realm. We see proof of a connection so profound, it rewrites our understanding of scale. It tells us that the subatomic jitters of virtual particles, the fleeting uncertainty at the heart of reality, were seized by the inflationary engine and magnified across space-time. Think of it. The delicate probabilistic tremors of quantum mechanics, a world governed by chance and ephemeral existence, became the indelible blueprint for cosmic structure. A whisper in the quantum foam amplified by inflation into a thundering chorus that would echo through the ages. Those slightly warmer, denser regions in the ancient plasma were the direct descendants of a quantum fluctuation that for a fraction of a second popped into existence with slightly more energy. Over billions of years, gravity would patiently amplify these primordial seeds. They became the gravitational anchors around which the first wisps of hydrogen and helium would gather the kernels of creation that would eventually blossom into the first stars, the first galaxies, and the vast glittering superclusters that form the cosmic web today. You, your world, the galaxy you inhabit, every massive structure in the cosmos, owes its very existence to a random quantum shudder in the first sliver of a second. This is perhaps inflation's most awe-inspiring revelation, that we are all quite literally creatures of the quantum void, macroscopic expressions of subatomic chance, sculpted by the most violent expansion the universe has ever known. This realization forces upon us a profound philosophical shift, a re-evaluation of our place in the cosmic story that is every bit as transformative as the Copernican revolution. We are discentered once again. The Big Bang is no longer the absolute beginning, the uncaused cause that sits at the edge of physics and theology. Instead, it becomes a mere exit point the moment our local region of space-time gracefully concluded its inflationary phase and settled into a more leisurely expansion, its stolen energy converting into the hot, dense soup of matter and radiation we know. Inflation is the mechanism that ignites the fuse of a Big Bang. It is the prequel to the story we always thought was the first page. This implies that the conditions of our universe, the physical laws and constants that seem so exquisitely tuned for complexity and life, may not be a fundamental property of existence itself. Instead, they might be the localized contingent outcome of how our particular inflationary bubble happened to decay. We are not necessarily living in the one and only universe, but perhaps in one of many a fortunate accident, with properties that just happen to allow for our own improbable emergence. This leads us to the most staggering, most mind-bending, and perhaps most unsettling consequence of the theory the multiverse. According to the mathematics of eternal inflation, the process once started may not be something that ever truly stops. While our pocket of the cosmos ceased inflating, dropping out of that high-energy state, the inflationary field elsewhere in the vast churning expanse beyond our horizon would continue its exponential doubling. In this grander vision, new universes, new bubbles of space-time are constantly precipitating out of the eternally inflating background like raindrops condensing from a boundless cloud. Our universe, with its trillions of galaxies and billions of years of history, would be but a single infinitesimal droplet in an infinite timeless ocean of creation. Imagine a cosmic foam seething with energy, where each bubble is a new universe. Each one could cool down with different physical properties, different fundamental forces, perhaps even different dimensions. In one, gravity might be so strong that it collapses back on itself in an instant. In another, it might be so weak that no stars or galaxies could ever form. Most of these universes would be sterile, empty, and dead. But in an infinite lottery, even the most improbable combination is not just possible but inevitable. Our universe, with its gentle constants and life-sustaining properties, might simply be one of the winning tickets. We exist here because this is one of the rare places where existence as we know it is possible. This is the Copernican principle taken to its ultimate conclusion. Not only are we not the centre of our solar system or our galaxy, but our entire universe may not be the centre of anything at all. It may not even be special. Its very existence and our own becomes a matter of statistical probability, a mere footnote in a cosmic census of infinite scope. This is a humbling and, for some, a terrifying prospect. It challenges our desire for uniqueness, for purpose, but it also opens up a vista of cosmic possibility so vast that it dwarfs all previous human conceptions of reality. Yet for all its explanatory power and its dizzying philosophical implications, the story of inflation is not over. It is not a closed book. The theory stands as a monumental achievement of the human intellect, but it remains a framework built upon pillars that we have not yet directly observed. It is a brilliant hypothesis awaiting its final irrefutable proof. This is where the true excitement lies. This is not ancient history, it is the frontier. The quest for that definitive evidence, the smoking gun of inflation, is driving some of the most ambitious and technologically audacious experiments ever conceived by humankind. Our cosmic detective story has entered its next thrilling phase, the hunt for the primordial messengers. The first place we look is back to that first baby picture of the universe, the cosmic microwave background. While its temperature map gave us the first clues, a deeper secret is hidden within its light, a property called polarization. The next generation of telescopes' instruments of breathtaking sensitivity like the Simons Observatory in the high Atacama Desert and the future CMB-S4 network are not just mapping the heat of the early universe, they are mapping the orientation of its ancient light. They are searching for a very specific faint swirling pattern in that polarization, a type of signal known as a B mode. These patterns are a unique signature, a cosmic fingerprint that could only have been imprinted by one thing, the gravitational waves produced by inflation itself. As space-time was stretched with such impossible violence, it would have rung like a bell, sending ripples of gravitational energy propagating through the fabric of the cosmos. These gravitational waves would have squeezed and stretched the plasma of the early universe, leaving a faint but permanent twist in the polarization of the light it emitted. Finding this signal is one of the holy grails of modern cosmology. It would be like seeing the tremor from the explosion itself, not just the flash. The search is excruciatingly difficult, requiring us to filter out the confounding glare of our own Milky Way galaxy to capture a signal so faint it is almost lost in the noise of the cosmos. But if we find it, it would be the definitive confirmation elevating inflation from a powerful theory to an observed fact of nature. But there is another way to listen for these primordial echoes. While CMB experiments look for the imprint of gravitational waves on light, a new window on the universe allows us to try and detect the waves themselves. This is the dawn of gravitational wave astronomy. The Laser Interferometer Space Antenna, or LISA, a future mission of 3 spacecraft flying in a triangular formation millions of kilometers apart, will be a celestial scale detector. It will be sensitive to gravitational waves with wavelengths so long they stretch across a significant fraction of the solar system. While its primary targets will be merging supermassive black holes, it may also be able to detect the faint stochastic background hum of gravitational waves left over from inflation, the resonance of that first moment still vibrating through the cosmos. It would be the universe's fundamental note, a sound produced in the first 10 to the minus 32 seconds, stretched by cosmic expansion into a gravitational hum with a frequency too low for any ground-based instrument to hear. Detecting this background would be like putting a stethoscope to the chest of the infant universe and hearing the lingering reverberations of its violent birth. It would be the sound of space-time itself being created. And yet, even if we find these primordial signals, a profound mystery will remain at the heart of the theory. What was the engine that drove it? What was the nature of the inflaton field, this mysterious hypothetical energy source with the anti-gravitational properties needed to blow up the universe? Was it a unique one-off phenomenon, or is it related to other known fields in physics? Perhaps the Higgs field that gives particles mass, or something even more exotic tied to string theory or quantum gravity. The identity of the inflaton is the great unknown, the ghost in the machine. Unmasking it will require a deeper union between cosmology, the science of the very large, and particle physics, the science of the very small. The answer likely lies at energies far beyond what we can achieve in our most powerful particle accelerators, energies that only existed during that first inflationary instant. The clues, therefore, are not buried deep within the Earth, but are written across the sky. The precise shape and nature of the signals we find in the CMB and the gravitational wave background will hold the key to understanding the physics of the inflaton. The cosmos itself is the ultimate particle accelerator, and by studying its largest structures, we are probing the most fundamental laws of nature. So our epic journey, which began by gazing up at a sky full of puzzling questions, now ends by looking both outwards and inwards. We look out to the farthest reaches of observable reality, and we look into the deepest, most fundamental nature of energy and space-time. We began with the mystery of a universe that appeared too flat and too uniform, and we arrive at the precipice of contemplating infinite other universes born from a quantum foam that may be eternal. The split second that created our universe did more than just set the stage for stars and galaxies. It established a profound and unbreakable link between the microscopic and the macroscopic, between the random flicker of a quantum field and the grand cosmic web that defines our existence. It continues to propel our quest for understanding, pushing our technology and our imagination to their absolute limits. We are a species driven by the need to know where we came from, to read the story written in the stars. And in the theory of cosmic inflation, we have found what may be the first explosive chapter. It tells us that our universe is the product of a physical process, that our structure is born from quantum chance, and that our existence may be one of many. We are the children of that ancient inflationary fire, a fleeting, thinking, wondering part of the cosmos, looking back in awe at the ferocious moment that made it all possible, a moment whose echoes still shape our reality, and fuel our unending search for our place within its grand and mysterious design.